So, Assalamualaikum. My name is Muhammad Akramir Aziz and my number matrix is 088632. And my team's member are Rasuluddin 087308 and Dinesh Daniel 088512 and Faris 087391 and Hafiz 086976. Today we will demonstrate two digital logic circuits, a 4-bit synchronous counter and a 4-bit register with load and clear. Both are designed in logism evolution using flip-flops and logic gates. These circuits represent how data is stored and processed inside a CPU.
Today, I want to present 4-bit synchronous counter. Okay, firstly, we need to turn on the enable switch. After this, we need to run the clock manually or auto toggle it. Yeah. Okay, when the clock pulses, the output count up in the binary sequence. Okay. The enable signal control whether the counter run or pause. The reset button clear the count back to 0.
Now, let's move on to the logic behind our 4-bit synchronous counter. In this circuit, each T flip-flop changes its state depending on the outputs of the previous flip-flops. All flip-flops share the same clock, so they toggle together in synchronization. The logic can be described using simple Boolean expressions. T0 equal to 1, this means the first flip-flop toggles every clock pulse. The second flip-flop toggles only when Q0 is high. The third one toggles only when both Q0 and Q1 are high. And the fourth one toggles only when all the lower bits are high. This AND gates connection between Q outputs and T inputs make sure that each bit only changes when the previous bits have completed a full cycle. When we observe the truth table, we can see the counter sequence clearly. It increased step by step from 0000 up to 1111. Then it returns to 0000 again. So this logic design ensures that our counter works accurately and synchronously, producing the correct binary counting sequence.
This 4-bit register uses the flip-flop to store binary data. The load signal controls when new data is stored on the next clock path. When the load is 1, it allows to store a new value to the flip-flop. When load is 0, the register holds the previous value. The clear button resets all outputs to 0 instantly.
Clear. Reset all outputs to 0 no matter what stored. Load. Loads new data D0 until D3 when active. If inactive, the register keeps its current value. The flip-flop inputs follow D0 prime equal to C prime period open bracket L period D0 plus L prime period Q0 close bracket, and similarly for D1 prime, D2 prime, and D3 prime. Clear equals 0 to outputs reset. Load equals 1, new data store. Load equals 0, 0 to all data held. This shows how the register store and updates data reliably, important for CPU and memory units.
To conclude our presentation, we would like to summarize what we have learned from this project. Our 4-bit
synchronous counter demonstrated how flip-flops and logic gates work together to perform accurate counting operations. By using logic evolution, we were able to visualize the flow of signals and understand how synchronous timing ensures all flip-flops change state together. This helped us clearly see how counting circuits play an important role in CPU instruction sequencing and overall control flow. In summary, counters manage sequencing and timing, while registers handle data storage, and both are essentials for smooth CPU operation. Thank you.